Okay, so thank you very much, Gunnar, and thank you very much to the organising, especially Renzo, for the making the fabulous arrangements for us to be in such a wonderful place. And challenge it is to try to concentrate on giving the talk when I could be taking photos from the upstairs. So I'm going to be talking slightly changed my title a bit. Is this screen share? I don't know if it's frozen, sorry. Okay, so I'm talking as a particle-like states of light from vortex knots to skyrmionic hopfions. So what I'm going to be talking about today is a topic that's quite close, touches on what several people have already spoken about yesterday, and other people will be speaking about after me, which is looking at vortex-like topologies and defect-like topologies in physical systems. But my physical system that I'm going to be talking about is light propagating in free space, just like this laser pointer here. And of course, if you look at a laser pointer, laser spot, one of the points of it is it looks like a point. It doesn't look like it has structure. But in order for light to carry mechanical effects, such as linear momentum and angular momentum, it has to have structure because it's not a physical object. It's not a material object, I should say. And so that structure has a topological nature, and I'm going to be talking about trying to understand that topological nature, both somewhat in natural light, but also in the way that we can control structured light primarily through holography. And I should point out, one of our heroes in the University of Birmingham is John Henry Poynting, best known for the Poynting vector, which of course is the direction, we could say direction of propagation of light. So I should just get a quick advert in before we get too stuck in. So I'm actually also the director of the so-called Centre for Doctoral Training in Topological Design in the UK. So we take in 10 PhD students a year, approximately, in this huge range of topics across engineering and physical sciences. And we're always looking for exciting young new PhD students who want to work in applied topology, applied in various different ways. So if anybody knows anybody who we take on international students, we're about to open for applications for 2023. Okay, so I mentioned Poynting, and this is one of my favorite quotations from Poynting. He gave this at an address to the British Association in 1899. So this is like the culmination of classical physics, just before quantum mechanics. And this is what he says. He's talking about what's the nature of physical science. And he says here, we explain an event when we know not why it happened, but when we show how it is like something else happening elsewhere or other when. We do not account for the event, but we approve our account of it by likening it to what we already knew. So I think that's very much in the spirit of this conference, where we're all finding analogies between different sorts of physical system and likening the effects that we see in our different systems to each other, and hopefully understanding them better. Okay, so I know that many people here aren't necessarily familiar with optics and light, so it's easy to think, I find it easier to think of light by trying to think of what are the various different descriptors of the different physical properties. And I'm mainly, as I say, thinking about light that's coming from a laser, so it's got a very well-defined temporal frequency, it's time harmonic. Obviously, electromagnetically, we think of it as an E field and a B field in a plane wave perpendicular to the propagation direction, or more generally perpendicular to the Poynting vector. Propagation direction we will always call Z or Z. A bit like we heard from Ben yesterday. But in general, what our physical electric field is, which is what we tend to measure, has has two spatial functions. I'd say this E here, I should have said, that can be dependent on position as well. So this psi, so we take the real part, here's the time with the frequency, and then this is a scalar function of position, a complex scalar amplitude, and this, so this is what determines, say, the phase and the intensity, and this is related to what the quantum wave function, the scalar quantum wave function, say in what Renzo was describing yesterday. So a plane wave propagating up the wave, the phases, which I'm representing by the hues, are just pointing up the page. But light can also have a polarization. So it could either be a constant polarization or a function of position, and that's perpendicular to the propagation direction. And in general, polarization is elliptic. So I've got some vibration in Y, some vibration in X, and they have a phase offset and can have different amplitudes. And so we represent those by a two-component complex, what we call complex vector or complex spinor, right-handed circular component and left-handed circular component. And of course, these two can be combined on a two-dimensional sphere, which in optics is called the Poincaré sphere. So right-handed circular straight up, left-handed circular straight down, linear polarizations on the equator, and the elliptic right-handed polarizations in the northern hemisphere, elliptic left-handed polarizations in the southern hemisphere. Mathematically, it's analogous to the Bloch sphere for a quantum spin or the Riemann sphere, but it's a useful way of representing the different polarization states, and the natural state space is this sphere. So when I talk about phase and polarization, these are the two things that I'm thinking about. So, and I'm thinking about say cylindrical light beams, so approximately what's coming out of the laser pointer is a uniform cylinder. But if it interacts, and I've got a bit of a poor man's demonstration here, let's see if it works. Shine it through an irregular surface like this water bottle. If I can you see it, the nice bright spot goes to become a smudge, and the smudge, if you look at it, actually has structure that you can see it changing if you move your head. And that structure, if you zoom in, looks like this sort of structure here, that you get little bright spots and dark spots. And that's called a speckle pattern. And you see speckle patterns all the time when you see lasers, because if the laser beam is reflected or transmitted through a slightly rough surface, you get interference, and this is the interference we're looking at. So when I talk about structured light, that's an example of structured light, randomly structured light. But here in the standard textbook on optics by Max Born and Emil Wolf, here what they have is a numerical solution of a light beam propagating through a focus, and these are the contours of the bright and darkness. Actually, these here are actually vortices, vortex rings that go round the focus. This is the propagation direction like this. So even around a simple focus of light in a lens, there's a very rich structure that we often miss because we're looking for the bright bits, not the dark bits. So you might think of a light beam being cylindrical, but if it's propagating along the cylinder, obviously there's no physical matter propagating along, so that propagation has to be described using phase and polarization. And similarly, if I want to do things like give this beam angular momentum, somehow that structure comes in through the phase and polarization properties. So here's an example of a transverse plane of light with varying phase and varying polarization. So at each different point, you can see a different ellipse. The gray is right-handed rotation, the white is left-handed rotation, and you can see in amongst these ellipses, there are these isolated points of circular polarization, and in fact, around the points of circular polarization, the ellipses rotate by plus or minus half. So these are a little bit like disclination defects in a liquid crystal. But they're described on this spherical space, as I said before, this Poincaré sphere. Often also we might fix the overall polarization and then just look at this complex scalar amplitude where, for example, if you put a 0 on the axis of a propagating beam, that 0 will stay there and the phase rotates around it like an orbital angular momentum in the phase, but that can swirl around in complicated ways depending upon how the beam is diffracting. But when we talk about optical vortices, we're really talking about these lines, which are zeros of the amplitude, places where you can't then define what the phase is, but they're also vortices of the energy flow that's swirling around them. So how would I how would I actually structure a beam? Well, in practice, most optics experiments start with a bright spot like this, which is, well, representing it here as a Gaussian in X and Y, which is a good representation of what comes out of a laser cavity. And then a hologram, effectively what that is that's like a complex scalar with both intensity and phase. I'm skipping some of the details, but so this is X plus IY here, and putting the hologram effectively imprints this phase pattern X plus IY onto this, it multiplies by it, and then it propagates through. So this is a bit like an initial condition in X and Y, and then it propagates through in Z or Z. And as I say, it conserves the angular momentum. So as the light propagates, you see this black spot in the middle, the so-called donut mode. Yes, that's an American donut rather than a European donut. But if you look at the phase structure, what you see is that you've sort of got these planes that are trying to line up, which are the planes of a plane wave, but then they coil around the 0, justifying it being a vortex. The surfaces of constant phase are all helicoidal. Of course, this is a straight vortex line, but a natural question is, can we take these vortex lines, these zeros, and tie them in knots? And of course, if we tie them in knots, that means that the rest of the phase structure has some non-trivial topology made up of Seifert surfaces through the rest of space. And so putting a vortex in the form of a knot has a global effect on the topology of the phase everywhere else. Okay, so that's it for my sort of little review of optics and light. I just want to say, given I'm talking about particle-like, I say this is partly inspired by Lord Kelvin's vortex atoms, as many of us are. But just as a reminder, Kelvin had the idea, almost exactly the same time as Mendeleev wrote down the periodic table, Kelvin had the idea that atoms might be knotted vortices in the ether. And so this is my artist's impression using our conventional modern knot table of what there might have been, but yeah, it really is just an artist's impression. So the idea is that different atoms are knotted vortex loops. So if we're talking about fundamental particles, what does this rely on? Why is this a good hypothesis? Well, one is obviously particles should be localized. And if we're talking about continuous fields, we're not going to necessarily localize them at points, but they're localized here as these sort of by the spatial extent of the knot. Somehow there should be some quantization of an atom. I shouldn't be able to have half an atom. So again, these being a single vortex loop defines that you have a particle. And there are lots of different sorts of atoms, and similarly any model of particles should be heterogeneous, and so we should be able to tabulate the different sorts of particles. And although, of course, Kelvin's conjecture was flawed, I'm going to carry these criteria to think about what we could justify calling something particle-like. Okay, so just to summarize so far. So I've talked about topological filaments in three-dimensional light, either as vortices, which are singularities of phase in a complex scalar amplitude, and disclination-like defects in the polarization structure, and they naturally occur whenever we have structured light beams. Topologically, they're analogous to vortices and defects in other systems people have been talking about, but they occur, in this case, in linear optical waves and carry no energy. So, looking forward, do not occur naturally in such wave systems, such as in superpositions of waves, maybe with random directions and random phases, which is a model of random scattering. So that's what I'm going to move on to by, let's look a little bit more at this optical speckle pattern. So this is actually laser light randomized and propagated through a ground glass screen. And this is an experiment that I did a few years ago with the optics group in Glasgow, led by Miles Padgett. So this is now a three-dimensional speckle pattern. So you can see the blobs, the potatoes are the regions of high intensity, but amongst them is this real tangle of vortex lines, zeros in 3 dimensions, with some of these are loops inside the volume, and some of them go through the boundary, and we don't know what they're doing. So you can ask, well, if I looked at a big enough volume, would any of these lines tie themselves into knots? And so this is like an optical analog of the question we heard yesterday about polymer systems. Polymer systems, we have a tangle of polymers, will they be knotted? Here, the question is about vortex lines in these linear random scattering systems. And so what we look at is, this is a simulation of this system, a 3-dimensional speckle pattern from a superposition of random plane waves. Now, as it turned out, our work on the speckle patterns, we weren't big enough. The simulations weren't big enough. But thinking instead at a slightly more mathematically definable system, what about thinking about the Schrödinger equation in a box, in some sense? So let's think about the eigenfunctions of a wave system like the time-independent Schrödinger equation in a box with periodic boundary conditions, or maybe a sphere, a 3-sphere in 3-dimensional space, or something else. So 2-dimensional analogs, just so you can see, in a periodic square, of course, it's very highly degenerate. So picking at random one of those very degenerate eigenfunctions in a square, here's the intensity and here's the phase, and you can see lots and lots of zeros everywhere in 2D. Here's doing it on the sphere with a random superpositions of spherical harmonics with the same energy, or in a 2-dimensional isotropic quantum harmonic oscillator. And so the density now depends on position a little bit. And here's a classically allowed region and the forbidden region, but you can still see this tangle of, well, all these vortex points, because this is a 2-dimensional system. But I can look at the 3-dimensional generalization of each one of them. So now moving to a periodic cube, or the 3-sphere. I'm just here, this is with stereographic projection going to infinity in 3 dimensions, but you can see it's sort of, the tangle is denser here than further out. Or indeed the 3-dimensional harmonic oscillator, and some of these lines go out to infinity, but they go in and they tangle themselves up and they go out again. So to cut a long story short, we did simulations. So this was with my former postdoc. We did many millions of simulations in each of these cases of just random wave superpositions and tracking all the vortices. And here's an example, in this case, of quite an interesting box. You can see that the blue line is, if you unwrap the periodic boundary conditions, is one long curve. And here is another curve here, this red curve. And this red curve here is actually a trefoil knot. And this is an energy 3n squared. So principal quantum number 9. So here's a trefoil knot, and it's 50 wavelengths long in this system. But the long blue curve, when you unwrap it, turns out to be this particular composite knot. A bit hard to see that it's knotted, but it is this thing with 2 trefoils and a 6 crossing knot in between, and its total length is 1700 wavelengths. So knotted vortex lines are possible just in random wave superpositions. Here's the 3-sphere, slightly different projection before. Now the 3-sphere is interesting because it's got a finite volume. And if you have a long vortex line, these actually the lines themselves are like Brownian random walks like we saw before. If the line as a Brownian blob would be bigger than the overall size of the sphere, it gets more and more tangled. So very long lines, vortex lines in the 3-sphere eigenfunctions can be very complicated knots. So this is some 14 crossing guy, but only 1500 wavelengths long in this simulation here. And here's a 3D oscillator. Now we can have long knots that aren't closed, but they still, well, they can be closed unambiguously, but are not actually physically closed. And so here, for example, is an example of the green guy in this 3D oscillator system. So just as a comparison, we plotted here the log of the knot determinants. I think yesterday the log of the determinant of the knot was used as a complexity measure. That was what we used as well. So this is a log-log plot against length. And you can see there are various straight line scaling relations. Here you can see that there are some very long lines that are still not knotted, but in the 3-sphere, because of this topological confinement I mentioned, that actually, if you have a very long line in the 3-sphere, it's almost certainly going to be a very complicated knot. And here it's somewhat of a hybrid between the two of them. So this is log length versus log-log determinant. A huge range of knots occur, and this data is for very many millions of knots. So cube has got some long simple knots, but the 3-sphere, the long knots are always complex, and in the 3D harmonic oscillator, there aren't so many very long lines. The smallest knot we found was in the 3D harmonic oscillator, open. It has certain symmetry, so it has this mirror image here. So this is in principal quantum number 4, but the probability we estimated of this one example we found in, I think, 30 million runs is a probability of 10 to the minus 7. But, and this is 2 open trefoil knots. Okay, so to summarize what I was talking about then with these random vortices, knotted vortices appear generically in random superpositions, or what we also called wave chaos, provided the volume is large enough, with a huge variety of knots occurring. Now, of course, what we're really talking about here is in each sample is in fact is a very complicated link, and we're just looking at single components. And we can find some small knots, but typically the large that we have the longer curves that tend to be knotted. But rather than thinking about what happens naturally just at random, I'm now going to think about what happens. Can we actually embed a given vortex knot by design into a propagating beam? So mathematically, what I'm going to be thinking about, and I've in fact always been thinking about, is a light beam very well the Maxwell's equations are very well approximated if I've got a fixed polarization by the so-called paraxial wave equation, where this is the Laplacian in x and y, it's propagating in the z direction, and this looks like the 2-dimensional Schrodinger equation with z like being time. And of course, what you can think of that is, as I take the laser spot and move it backwards, that's like a Gaussian wave packet spreading in time. And so this is just a linear wave equation, so any beam can be represented as using a superposition of an appropriate set of basis functions. A good set of basis functions in cylindrical coordinates are the so-called Laguerre-Gauss modes. So this is, I've just taken the function in the z equals 0 plane it's got a Laguerre polynomial in radius and an e to the IL phi vortex up the axis. So these are natural vortex carrying modes. So here LG10 is our basic donut mode that I showed before with a single vortex line up the axis. Here's 2, 1, so I've got a double vortex on the axis with this 2, and this 1 means that it's a first order Laguerre polynomial. So I have a 0, what would be a 0 on propagation, a 0 cylinder. But this thing isn't stable. If I were to perturb it, I just kick it, I have some imperfections, what I get has to become topologically stable, and what I get is a network of vortex lines with just a 2 pi phase quantization. So the question is, can we engineer complex waves with knotted 0 lines? And when I tried to answer this question some years ago, I was led to questions that were investigated by pure mathematicians such as Browner from about 100 years ago and John Milner in the 1960s, whose questions could be paraphrased or can be answered. Their questions answer the question, can we construct a complex scalar field from R3 to C with 0 lines in the configuration of a given knot or link? And Browner answered that question for torus knots. And if you look in the books, they say, oh, well, the solution for a MN torus knot, it's a two variable complex polynomial, u to the m minus v to the n. So here is the trefoil knot that I talked about before. So what's not quite clear, if you don't quite come from the same background, what's the relationship between this and a function of x, y, and z? But that's what we tried to understand, and also generalize construction away from just these torus knots to be any knot or link. And then from that, can we actually embed that into a light beam? So it only works with torus knots. So here's Tate's knot table. You can see there are lots of knots here that are not torus. But we were able to, well, me and a succession of PhD students have been able to understand it by thinking about the relationship between these polynomials and a braid representation of the knot. So a classical representation of a braid that Mitch mentioned yesterday is thinking of the pigtail braid. So you braid someone's hair with 3 plaits. That's what the zeros of this phase field are doing. And each of them are following this lemniscate pattern, this figure 8, or this infinity shape. And so we can construct a complex scalar function with the zeros of a braid here by thinking of each of the slices. So time here is like the height of the braid, and then the transverse plane to that I'm thinking of as the complex plane. So we can create any braid we like by taking height as a parameter for the zeros of a polynomial that in variable u. And the idea becomes that you can then take that braid, in this case I've got a double helix braid, and make the replacement that e to the IH, or e to the IH on 2 here, becomes this other variable v. And when you do when you decide how many repeats of that basic braid you want before you close it up, and so then this polynomial pH of u after this replacement indeed becomes that Browner-Milnor function. Then representing u and v as x, y, z in the 3-sphere, like Ben Boda mentioned yesterday, effectively closes this braid to give us, in this case, a trefoil knot. So this is at least my explanation of how that Browner construction works. And you can generalize it. So now here's the pigtail braid realized here, and here's the what the complex zeros are doing. The same operation, but now because we've got twisting both clockwise and anti-clockwise, means we don't just have e to the IH, we've also got e to the minus IH, so it needs to have both V and conjugate V. So the two variable polynomial ends up being involving V and its conjugate, but still only U, and it's cubic in U because of the 3 strands. Same operation, this braid closes up to the figure 8 knot. So that's a way of constructing complex scalar functions. How can we get those into a light beam? Well, we don't really have a systematic theory, but if you take a slice through the middle of this function, so like a slice through the middle of the bagel or this donut, you get this complex scalar function. Being a bit explicit, this is it in radius, it's 6th order in radius. This bit is all just axisymmetric, and then there's this extra bit here with the 3I phi here, and you put it all together and you get these 6 vortices. Here, put that in as the hologram. Oh yeah, so this is an axisymmetric bit and an orbital angular momentum bit. Put that into the hologram. As it propagates, it gives a trefoil knot in this case. So this is a way of getting, and this is the decomposition in terms of the Laguerre-Gauss modes of this that's come out of this procedure. So, and then this could be embedded in the experiment, and this was our experimental trefoil knot. So working with, well, as part of his PhD thesis a few years ago with me, Ben Boda, we proved a general theorem that can realize every knot and link as the nodal set of what we call a semi-holomorphic complex polynomial. So it's got U and V conjugate there. And the idea is generalizing what I said before, that you can write your braid as in X and Y as a Fourier series, and you either construct it algorithmically or sort of a little bit ad hoc by looking at what the braid's doing. So this finite Fourier series looks like this, which is actually the minimal braid word of the 3-twist knot 5-2, and go through the same procedure, but just being a little bit careful on the way that you're embedding it, that effectively the parameters of that torus that I was folding over before. So long as you're careful enough, you're able to show that you will always be able to make a complex scalar function with the knot as the closure of this braid in 3-dimensional space. So here are some other examples of things we did with the sort of braid trajectory in each of the cases. Which of these are possible in light beams? Well, it turns out we're a little bit more restricted. Of course, we don't quite understand the mechanism that we're using that's coming up here. So we don't quite understand the restrictions of the paraxial wave equation. There's no energy, so it's very hard to sort of get a handle on stopping the vortices from reconnecting and doing the wrong things. So for example, taking this 3-twist knot function, slicing it through the middle to give us a hologram, and then propagating it does not give the right topology. In fact, we get 3 unlinked rings. So we need to be cleverer in a way that we don't understand. But the construction seems to work at least for the family of lemniscate knots, where the braid is built up by what we call lemniscate knots, where the braid is built up by some sort of iterated lemniscate like this, which can give relatively complicated functions like this, which is 818, as used on the logo of the International Guild of Knot Tiers. So I've just sort of given a very sort of, the description I've given is a sort of trying to, where maths meets optics in a sort of simplest way for both of them. You might think for maths there are natural questions that would go beyond optics, but similarly in optics there are natural approaches that go beyond thinking about just nodal lines. And one particular limitation in experiments is it's very hard to measure phase patterns when intensities are very low. You've got a lot of noise, you've got other things going on. So actually to get a very good picture of what all of the structure of these knots are, rather than looking at phase, it's actually nicer to look at polarization. So so this is an approach done with the group of Abraham Skyrme in Ottawa, where we took the same sort of functions that we took before, but now rather than looking at vortex lines, we're looking at lines of where the polarization is circular and everywhere else it's elliptical. So now it's roughly uniformly bright, and the measurements, instead of using interferometry, use polarimetry. And so here's a measurement of actually the figure 8 knot, which was a knot that we were never able to generate experimentally with the pure phase vortices. And we were also able to construct quite a lot of the Seifert surfaces for these and see, well, they're actually really quite complex. They have quite a lot of extra topological structure. Okay, so design knotted vortices. We can create complex scalar fields for any knot or link based on Fourier representations of braids. We can turn them into holograms, and at least sometimes they work to give us knotted vortices. But moving on to my main point of saying, what about particle-like behavior, not just Kelvin-like knots? We led my former student Danica Sujic and I to think about topological textures, where we're not just thinking about special isolated lines, but thinking about the entire field of polarization ellipses. So that led us to think about topological solitons, which, well, there are some experts in the audience here, and I apologize for my crude characterization of them here, though I do have to mention that they're named after, well, skyrmions are named after Tony Skyrme, who was a professor at the University of Birmingham, where I am, who was thinking of these as actual explicit models for nuclear particles in high energy physics. And in general, I'm going to characterize what the skyrmion as a particular sort of map. Well, this is a 1D skyrmion, a particular sort of map from n-dimensional Euclidean space to the n sphere. So in this example of 1 dimension, I've got 1-dimensional line here, and it's mapping to the circle that I'm representing here, but also using colors. And of course, you can put it, if you fix the boundary conditions here, the number of windings is topologically protected. And so the envelope here is what I'm calling the Skyrme density, which is the Jacobian of this mapping. So the rate of change of the angle with respect to position here, you can see it's pretty much constant, and then it has this isolated winding here, which integrates to +1. And this idea generalizes to any dimension. And so, and you find the Skyrme number, the degree, the winding number, or its generalization, by integrating this function over the real space. So, in a sense, this satisfies the criteria of being a fundamental particle. It's localized in this case, and I've not put any of the details in, because this actually satisfies a particular energy functional or nonlinear energy functional. It's a nonlinear soliton. So that's what deals with the localization. The quantization is handled by the topological degree of the mapping, and it's heterogeneous because of the different winding numbers. So going from 1D to 2D, we're thinking of planes, and within the plane, you've got arrows, and those arrows can point anywhere on the sphere. So here, the background, they're all pointing up, but within this disk, they point everywhere on the sphere, with it pointing straight down in the middle. So this is an example of what we call a 2-dimensional skyrmion, and you can think of it, the mapping from the plane to the sphere, maybe the way that you might wrap up a spherical present with planar wrapping paper, or stereographic projection, or mapping the Earth to the plane in some way. The Skyrme density now is that expression, where S is our unit vector. I should say this is this simple idea, but put into magnetic systems is receiving a huge amount of attention in so-called skyrmionics, which is a branch of magnetic spintronics where the arrows are little magnetic arrows, and these skyrmions are actually then could be topological bits in for computer memory, and they can be pushed around with currents and could be solutions for low energy memory computing in the future. And it's possible to get high, this was an experiment in liquid crystal, but you can get high degree skyrmions this way as well. So people in optics have been taken away by this idea as well, although I hesitate to say they're calling them skyrmions. These are not nonlinear. These are just, again, solutions of linear systems. So I'm hesitating to call them skyrmions, so I know that Paul will beat me up later, but this is what it takes to get published in Nature and Science these days. So this first experiment reported a few years ago, they talk about this was what they're calling a skyrmion lattice. This is in the E field in the surface above of a constructed metallic wafer. And you can see these sorts of, the E field is pointing up here and down here in the way I showed you before. Or the direction of optical spin was done this way. So this is now the normal to the polarization ellipse, pointing in all directions, giving us a 2D baby skyrmion. Or taking the Poincaré sphere as the target space, so-called full Poincaré beams that realize all states of elliptic polarization in the plane, again, can be thought of as skyrmions in different ways, depending upon what you're thinking of as your main order parameter. And people are even now calling these skyrmionic beams, and the beam design is relatively simple. You have two components, a right-handed component and a left-handed component. Say I put a vortex in left-handed, no vortex in the right-handed, across the plane, that will realize all the polarization ellipses, so we'll wrap around the Poincaré sphere. But I want to think about the 3D case. So to think about the 3D case, we need to understand the anatomy of the 3-sphere, which I know is very familiar to some of you, but maybe not to everybody. So how can we visualize a 3-sphere, a sphere in 3-dimensional space? So one easy way of doing it, as we've said several times already, is we can think about stereographic projection. Take away a point, send it to infinity, and then everywhere else here in 2D, but we could imagine in 3D, becomes a point on our 3-sphere. And so long as I'm converging to the same point as I go in every direction, that's okay. So therefore, I could start from an origin. I've got my usual theta and phi spherical polars, but my radial coordinate becomes the third angle in hyperspherical polars. Now, so that's one way of thinking about it, but another more useful way is thinking that the 3-sphere, unlike its lower dimensional analogues, supports the so-called Hopf fibration. So Hopf fibration, you can imagine having, well, this is a link with the point, this is a point at infinity here, and here's a black line. And so this, around this link, we can build a texture of loops, each of which is linked with each other and these two. And each of the loops, well, so starting with these 2 points, I can think of parameterizing them by points on a sphere. This one is this point, this black one is this one. And then cutting up the rest of this 3-sphere into tori around this thing. And on each torus, I draw a 1-1 torus curve. And so the torus radius is related to the angle down here. And my azimuth around here is my azimuth around here. So you can see as we go up, we can build more and more, cut this space in, so each point of the 3-sphere lies on one of these circles, which is parameterized by a point on this sphere. So that's a fiber bundle, the so-called Hopf fibration, where the fibers are circles and the base space is this sphere. And that has led to people thinking about things which are hopfions. that is to say structures in three-dimensional space of closed loops parameterized by points on spheres, or using that as a way of parameterizing things that really live in the three-sphere, where we actually have that, where we're using the coordinate on the sphere as well. So Penrose has used this in his twistor theory. Structures like this have been suggested. Couldn't resist this, putting it in the Dirac equation, given how much we have the Dirac Museum next door. And that's by the group of Iwo Bieleninsky Berula in Warsaw. Liquid crystals can show these structures as well. These are measurements by a group of Ivan Smalyuk in Boulder. And well, this was a collaboration with Paul and some experimentalists where they realized hopfions in magnetic multilayers using a similar argument. But also skyrmions, where you actually include the phase. You're really thinking about the coordinates in the three-sphere, and that those occur in BECs in various models of high energy physics, and a few years ago were demonstrated experimentally in a BEC. But how does that work in optics? Well, in optics, if you think about it, just with the phase and polarization, we have what, because no one else seems to have named it anything, I'm calling the optical hypersphere. So if we think of our polarization little 2D vector, that has a real part, an imaginary part for its right-handed component, real part, an imaginary part for its left-handed component. If we normalize, in fact, all of the possible polarizations are the coordinates on a three-sphere, a sphere in four-dimensional space, so long as we normalize. So if I think of the right-handed component and the left-handed component in terms of polarization parameters, so the ellipticity of the polarization ellipse, the angle of the polarization ellipse, and the overall phase, that gives me three angles that parameterizes these things here. But in fact, those three angles are precisely the angles parameterizing the Hopf vibration. So the ellipticity and the azimuth in this three-sphere space determine the circles of the Hopf vibration, and the coordinate along each of these circles is given by the overall phase. So the optical hypersphere, as I'm calling it, naturally realizes the Poincaré sphere as that spherical base space of that three-dimensional fiber bundle. And so this led us to say, well, with thinking about these structures, we were able to construct what we are calling a skyrmionic hopfion in a three-dimensional light beam. That is to say, realizing the hopfion-like structure in polarization, but the skyrmion-like structure of the full three-dimensional three-sphere, where effectively what we're doing is we're realizing every ellipse with every possible phase within a finite volume of space. And within that volume of space, the polarization and phase structure seems to reconstruct the Hopf vibration. So this is our measurement of our real space light beam. It's got a sort of up the middle here, it's got a line of right-handed circular polarization. Here, are in the focal plane, there's a circle of left-handed polarization, and around it there are filaments of fixed polarization and varying phase all the way around. So filaments of fixed polarization are loops, and the loops lie on tori of the same ellipticity, and they lie between these filaments of right-handed and left-handed circular polarization. So for example, here's the torus made up of linear polarizations, and each pair of these loops is linked. Here's a different torus of fixed elliptic polarization of a fixed ellipticity. And there's the right line of right-handed circular polarization up the axis. So as I say, we call this a skyrmionic hopfion. In a sense, what it is, it's a mapping between here's real space with this Hopf vibration, and here's the idealized parameter space, the optical hypersphere, where all of the filaments here are nice circles, but under this mapping, here our flat planes become deformed sort of objects. And our Skyrme density, this Jacobian, measures the deformation of volume from real space to the hypersphere. So as it happens, this beam design that we've used has quite a high density close to this loop here. So this square goes to become, well, this cube becomes quite big, but elsewhere it goes to be quite small. So say I'm skipping the details of the beam design. The basic structure is right-handed component has a vortex up the axis, left-handed component has a vortex round here. But there's a lot of extra design that's gone into it that really brings in all of these polarization and phases within the measurable focal volume. So the degree of the 3D skyrmion is into integral overall space of this 3D Skyrme density involving the vector in 4-dimensional space. But we can rewrite it in terms of our parameters for the Hopf fibration, and in fact, as it has to, can be re-expressed in terms of a helicity. The helicity in this case being the so-called orbital current, the current of the pointing vector, but not including the spin, the contribution from the spin current. It's a pure orbital current that gives the helicity in this case, because I haven't really taken the full geometry of the polarization into account. Here's experimentally measured Skyrme density. It's sort of approximately this ring. As I said, with this most concentrated around the black loop that we had before. And if you add up the amount that we're filling the 3-sphere, this is a 3-sphere within a finite volume, we almost completely fill it. There is a bit of experimental error. The theory within the volume we've taken is 0.997, but experiment we got 0.945. So, sorry? Well, so what I've done here is I'm taking a projection of the optical hypersphere, and I'm saying how much of the optical hypersphere is filled. So I'm putting the optical hypersphere within a ball. Now, I haven't shown you what the radius of the full hypersphere is, but it really goes out to the edge here. As I say, it's 0.9, fills 0.945 of the volume. So, and I should say, I'm not going to go into any details, but working with group of Yanuros, Tarkowski, and Lancaster, we've been looking at how we can embed these things into atoms, and as well as that, looking at higher order skyrmions, where we start with knots and so forth in the one of the components rather than just having a loop, and that's enabled us to get higher degree. So we've realized a 3-dimensional skyrmionic hopfion in a propagating beam, realizing almost all states of optical hypersphere, polarization and phase within a finite volume of the propagating light beam. The polarization texture in real space resembles a Hopf fibration, where the fibers are filaments of fixed polarization, and we can ask, is that particle-like? So localized here comes from our beam design rather than being a nonlinear soliton. But the quantization, okay, we measured 0.94, which is pretty close. And heterogeneous comes when we combine it with knots. Now, I'm out of time, so I can't tell you about the natural optical system which we found where these skyrmionic hopfions seem to appear, but I will say it turns out to be in the focus of specific sorts of beams. They were always there naturally, just no one thought of looking for them topologically like this. So in summary, we've seen light form of various sorts of particle-like knotted and linked topologies, both naturally and in holographic beam design. And I'd be very interested, anyone's got any suggestions, what other sorts of topologies might we try to realize in light beams? The most important or pressing application would seem to be finding ways of now understanding this topologically structured light in interactions with structured matter, and maybe seeing new sorts of topologies arise or controlling, using light to control topological structures in different sorts of matter. And I want to leave you with, from the same source I had before, this is pointing again. So as we watch the weaving of the garment of nature, we resolve it in imagination into threads of ether spangled over with beads of matter. We look still closer. The beads of matter vanish. They are mere knots and loops in the threads of ether. Thank you very much.